Let's consider the x and y coordinate plane. For any point on the coordinate plane, we can identify its location by assigning coordinates to the x and y positions. So we can assign a horizontal coordinate and a vertical coordinate. So for example, point A has coordinates of 4 and 3. The idea of symmetry can help us describe relationships between different points on the coordinate plane. For example, I'd like to consider 3 different types of symmetry. We describe points as being symmetric with respect to the x-axis if they're sort of balanced, if their position is balanced across the x-axis. Relative to the point A, the symmetric point would be exactly on the opposite side of the x-axis and the same distance away from it. So the coordinates for that point would be 4, -3. In general, we can describe the relationship of symmetry with respect to the x-axis by associating the generic point x, y with its symmetric partner x, -y. Because for 2 points to be symmetric across the x-axis, the x-coordinate is going to be exactly the same, and the y-coordinate is going to become exactly the opposite coordinate. So in a similar way, we can talk about symmetry with respect to the y-axis. Given a point x, y, or more specifically, given a point 4, 3, the symmetric point is going to be exactly across from it, exactly across the y-axis from that point. And so the y-coordinate is going to stay the same, but the x-coordinate is going to become exactly the opposite. So point C, for example, would have the coordinates -4, 3. And that would be the symmetric partner with respect to the y-axis, the symmetric partner to point A. So in general, we can say 2 points are symmetric with respect to the y-axis when they have coordinates that look like x, y and -x, y. A third type of symmetry relates to symmetry with respect to the origin. The point A, the symmetric partner to that with respect to the origin, is going to be on the opposite side. So it's going to be balanced, in a sense, balanced with respect to the origin. So we can think of going in the direction of the origin and then that same distance beyond it to get to the symmetric point. And so point D, if it's symmetric with respect to the origin to point A, it's going to have coordinates that are exactly opposite, -4, -3. In general, when points are symmetric with respect to the origin, their coordinates are going to look like x, y and -x, -y. With what you've seen in the video so far, I encourage you to pause and think about the following question. What are the coordinates of the point that is symmetric to -2, 7 with respect to the x-axis, the y-axis, and the origin? After thinking about that question for a little bit, try to come up with an answer and then restart the video, and we'll take a look at what it means for a graph to be symmetric. Graphs can be symmetric, and we think of a graph as symmetric if it's balanced in the ways that we've talked about. So let's consider the graph of y equals x squared. I hope this is a pretty familiar graph. If it's not, that's fine too. The graph of y equals x squared is going to be a parabola, a U-shaped graph that passes through the origin. And if you think about the symmetry of this graph, would it be best to call it symmetric with respect to the x-axis, the y-axis, or the origin? Well, I hope you agree. It's symmetric to the y-axis. And the reason why, if you think about a point on this graph, for any point on this graph, the x and y coordinates of a given point are going to be partnered with, on the other side of the y-axis, negative x and y. Right, the y value is the same for x squared and negative x squared, because squaring cancels out the negative. So we can say the graph is symmetric with respect to the y-axis. More generally, if we think of this as the graph of a function, if we think of the function f of x equals x squared, I could call this function symmetric. I could say the function is symmetric across the y-axis. And when that happens, we call the function an even function. Even functions are symmetric with respect to the y-axis. Odd functions also have a certain type of symmetry. Odd functions are symmetric with respect to the origin. An example of such a function would be like g of x equals 1 over x. Thinking about the graph of that function, it has a piece of positive values they go up to infinity close to 0, and it has a negative section. It goes down to negative infinity close to 0. And so any particular point, like if I plug in 2, the value is 1/2. The y value would be 1/2. And if I plug in negative 2, I get exactly the opposite value. The y value would be negative 1/2. And so there's a balance. My sketch doesn't really give it justice, but there's a balance to the points on the graph where any given point is going to have a symmetric partner that's exactly across the origin from that point. So we say a graph is symmetric, a function is symmetric if every point on the graph has a symmetric partner. Let me end with a question. Think about the idea of functions and symmetry and try to answer the question, can any functions be symmetric with respect to the x-axis? I hope you enjoyed the video. Thanks for watching.